So hi everyone. I'm Marwan Abbas. I graduated from the American University in Cairo back in 2021, and I'm currently working with eFabless as a EDA and IC developer. And today we're gonna be talking about verification of your design and OpenMPW submissions. Um, so before we go through verification and open MPW submissions, I just want to address one advanced feature in OpenLane that actually would help a lot with starting your design and developing your design. So this advanced feature is actually very useful when you're starting your design. Before synthesis, which is the first step OpenLane does, um, you can specify which synthesis strategy you want to use. So there are different synthesis strategies, and they're oriented to two different orientations. So it's either area oriented or delay oriented, and that's very specific to your specific design. If your design objective is to have like a minimal area design, you can go ahead and use an area-oriented synthesis strategy, or you can go and the delay is used when you want to have a faster design or a delay-oriented design. So actually, I'm going to show you how to do that. So the command here is the command that you can use, and this is gonna do synthesis exploration on your design, because you can this feature basically does all the different synthesis strategies, because you have four in the area four in the area orientation and five in the delay orientation. So it gets you it performs the synthesis strategies for all the strategies, and provides a summary report. So if we go ahead and go into OpenLane, I just make mount inside OpenLane and run this command design. So I'm gonna run it on the SPM, and I'm gonna give it a tag, so the run has that specific tag, so that I know which run it is, and I'll give it the flag, which is synthesis explorer, and run it. So it's gonna take a couple of seconds here. Oh, I got it wrong. Explore. So overwrite is just to override the tag.
There is a spelling mistake.
Yeah. So it's running synthesis exploration. Give it a couple of seconds, and it's gonna. Yep. So it's done. We can. So this report is an interactive HTML report. So we can open it up using Firefox, for example. Okay. So here you get all the different strategies, and the gate count, area, delay, and the ratios between them, and a graph between that. You have the area on the x-axis and delay on the y-axis, and actually here on the top you can see that it's giving you which is the best strategy for your design, best area strategy, best gate count strategy, and best delay strategy. So this report is actually very useful when you're starting up your design, and you wanna know which synthesis strategy you wanna use. You can use this feature in OpenLane. So I think it's good to highlight it, and that's why I wanted to highlight it. So going back to our presentation. So this is the report that we just saw. And now we can go ahead and dive into verification. So verification is actually one of the crucial parts of ASIC design, and it's actually the part that has all the engineering and all the design methodologies. Because yeah, you've done your design, you've went through OpenLane and everything, but how do I know that this design works? How as a designer, how do I know that this design works? So verification, we have three types of verification. We have functional verification, physical verification, and timing verification. And if you see here in the diagram that actually Dr. Shalan showed yesterday, the functional verification is outside the OpenLane flow. So OpenLane doesn't do any functional verification, but it actually does physical verification and timing verification. So functional verification is a part that the designer needs to do on their own. We're providing the tools and the methods of how to do functional verifications, but it's mostly the designer that needs to do it. It's not done out of the box in the OpenLane flow. So diving deep into the functional verification, why do I need to do a functional verification? So I need to verify that my design works, first of all, works in general, and then works in the context of Caravan. So there are three types of functional verification, or actually two types, and we run one type twice. So we have the RTL simulation that's done typically before even going through the OpenLane flow. So as you can see here in this diagram, the RTL verification is done first before anything. Once you've written your Verilog code, once you have your design, you should go ahead and start your RTL verification to actually make sure that your design, the Verilog code that you just wrote, is working correctly, and is executing the functionality of the specifications correctly. And then there's the gate level simulation. So if we go back to this diagram, we're gonna find that OpenLane, actually one of the files that it emits is a gate level netlist. And the gate level netlist is basically the RTLs. It's a synthesis of the RTL. So it's your design done in standard cells. So it's a netlist that has standard cells that's coming from the technology or coming from the library, the PDK. And why do I need to do that verification? It's because OpenLane, at the end of the day, is a piece of software. So it might have a bug, or any other piece of software that you're using, it might have a bug. So I need to make sure that the gate level it emits is actually a real functional gate level, and it reflects what I've done in the RTL, what I've wrote the design to do. So that's one thing, and the other thing is it can uncover bad RTL modeling. So when I'm writing RTL, some things might work with the RTL, but it shouldn't work with a gate level netlist. And then the last verification that we typically run is gate level plus SDF simulation, which is a standard delay format file. And we're gonna dig deep into that later in the presentation. So I don't want to go into too much details here. So the more reason to do gate level verification is that actually through OpenLane's flow, this gate level netlist is actually getting updated. So there's insertion of clock trees. There's antenna diode insertion, so that you don't get any antenna violations. And there's timing optimizations, and so it's inserting buffers. It's resizing. It's doing cloning to the gates. So So it's very important to make sure that that OpenLane did not break the gate level netlist while doing these updates, because maybe it inserted a buffer somewhere that broke your design, or something similar. And something to note here is that because the gate level netlist is very complicated, and it's actually more complicated than the RTL that you ran before. It takes significantly more time to run the simulation for gate level verification. So as mentioned before, we have a third type of verification, which is the delay annotated gate level verification. So if you think about it, RTL simulations have zero delays. So there are no gates, so there are zero delays on the gates. Okay. And the gate level simulation, yeah, you have gates, but all the gates have constant delays. So it's the designer that puts in the constant value of the delay gates. So of the gates, sorry. It doesn't make it, this is not the real, like this doesn't work in real life. So you need the actual delays, which we get from the Liberty files from the PDK. These Liberty files have the delay models of the gates, and then we use open source tools to generate standard delay format files and standard parasitic extraction format files. And the SPEF, or the standard parasitic extraction format file, uses the resistance and capacitance values of the nets to extract and to get extracted. So here we have the delays, we have the gate level netlist, we have the delays of all the gates. So we can run the verification with actual delays that's coming from the PDK. So it's coming from the fab that's manufacturing the chip. So we know that these are real delays. So we should expect to have somewhat of real simulations. Like simulation is simulating what's happening in real life. So so this is the closest thing that we can get using simulations. And so the SDF annotated simulation might uncover some timing violations. And these timing violations leads to unknown circuit states. So typically the simulation should fail if there's a timing violation, but in some cases it doesn't, because this unknown state might be the right state. It might be, but that doesn't mean that you don't have a timing violation. And that means that if you have a timing violation, then you have a problem. You can't just say that I have a timing violation, but the simulation works, then I'm fine. No, that's not true, and you might get back the silicon and it has an issue or a bug. So we have 4 types of timing violations. We have setup timing violation, hold, recovery, and removal. So to go through them really quick, and just to give an overview of the different types of violations. Let's say that you have let's talk about the hold and setup violations first. So let's say that you have a flip-flop, and this is the input, the output, and the clock. Okay. So the setup, there's this time, the window before and after the clock changes. So the clock is changing from 0 to 1 a certain amount of times per unit time. So there's a window before and after the clock changes that the data should be stable. So if the data changes before the clock inside that window, that means that you have either a setup or a hold violation. So the setup window is before the clock changes, and the hold window is after the clock changes. And actually, it's seen here on the bottom right image. This is the earliest that the data can arrive or change in general, and this is the latest it can change. So so it can change in these windows, the yellow and purple windows. If it changes there, then you have an issue. You have a timing violation. And then we have recovery and removal timing violations, which are basically similar to hold and setup violations, but they're more concerned with asynchronous reset signals. So you typically see these violations when you have a reset signal, and if the reset is changed through over these windows, not outside of them. So anything outside these windows is okay, but if it changes inside this window, then you have a timing violation, or you have an issue. And then there's, if we go back to, so we've talked about functional verification. We now want to talk about timing verification. And actually, timing verification is done through OpenLane flow, and it actually emits timing reports, which we're going to talk about later in the presentation. So yeah, so static timing analysis, or STA. Which is the timing the timing verification that's done through OpenLane flow, does not depend on any data being applied in the design. So it basically gets it basically breaks the whole design into paths and calculates the signal delays along these paths. And then when it calculates them, it checks for violations inside the design and on the I/O ports. So the paths can be seen here in the diagram below. It's input to register, register to register, or register to output, or input to output. So actually, you can change the constraints on the I/Os. So you can actually, if you have a violation here, you can change these constraints so that you can relax the constraints a bit, so that you don't get a violation. But yeah, you can get that from the STA reports that that OpenLane emits. And actually, whenever you have an STA violation or a timing violation when using STA, OpenLane is gonna actually break. It's not gonna complete the flow. It's gonna tell you that you have a hold or a setup or a recovery removal violation. And this is the typical error that OpenLane emits when it breaks the flow. And you can look at these reports that actually OpenLane tells you about, and you can then find out which path is it, and how to overcome that timing violation. And then there's the SDF gate level verification, which emits a log as well. And we're gonna tell you how to run the SDF gate level simulation. That log will probably, like, the simulation will, as I said before, the simulation will probably break. But if it doesn't break, you need to actually check that log and make sure that you don't have any timing violations. So the timing violations typically look like this. So you have the time where the violation happened, the test bench that you ran, or the tests that you were running on the design, the block name, and the instance name. So for example, it's here the block name is, for example, if you're running SPM, it's going to be SPM, and the instance name is going to be the exact cell that has the issue. And then here you're going to get whether it's setup, hold, recovery, or removal violations. And then it's going to tell you between which signals did the violation happen. That's typically between like a clock signal and a data signal. And then it's going to tell you the supposed window that it should have happened. And then this diff is just this minus this. So it's going to tell you how much is the violation. Okay, so moving on to how to do simulations, how to do the functional verification. So in the Kervel environment, or the Kervel user project environment, you have the test benches separated into two files. You have the C code, which gets compiled and runs firmware on the CPU, which is inside Kervel. You don't have to think about it. The CPU is below your user project inside Kervel. So the C code is the firmware that's gonna be running on the CPU to tell it which exact registers it needs to access and which commands it needs to execute. And then you have the Verilog, which interacts with the test that's being ran on the compiled firmware. So for if you think about it, basically the Verilog test bench is what you're gonna do if you have the board in your hands. So for example, if you want to click on reset, then you're gonna write that you're gonna reset the board in this Verilog. So if you wanna for example power up the board, then you're gonna write that you're gonna power up the board in the Verilog. So it's kind of the how you're gonna do the test if you have your if you have the chip in your hand. So in the Kervel environment, the test benches are actually constructed in a way that tests the specific functionalities of the design. So we have each test bench doing one specific functionality. We don't have like a big test bench that does all the functionalities. And actually, we encourage that you have all the test benches running and passing all gate level SDF, gate level and gate level with SDF and RTL simulations before tape out, so that you make sure that your design is bug free, timing clean, and you don't have any issues with your design, so that when you get back your silicon, it doesn't have any problems. So let's try to go ahead and run a simulation on our design that we hardened yesterday with Ziad in the first hands-on working session. So now I'm assuming that you have the gate level, you have the GDS, and you have everything that you need for that for that user project. So we're gonna be simulating a test that basically gives like puts values in the multiplicand and the multiplier, and then we're gonna test how the product is gonna look like. And actually, I sent you these files over Slack. So if you didn't, I'm gonna give you like a few minutes. Like I'm gonna pause for a minute or two so that you can download them. They're on the channel so that you can go along with me. I think I'm gonna go ahead. So if we, so if you have the files that I just sent you, you should have this Wishbone SPM file, and you can go ahead and copy that file and put it inside Verilog DV. So that's typically where we put our test benches, and I'm gonna show you what it looks like from the inside. So you have a make file. That's a standard make file that is common between all the test benches. So you can just copy paste it from any test bench you want. And you have a C file and a test bench file and a Verilog file. And actually, we're gonna look at it, but this test bench specifically is actually a copy of the Wishbone port test bench. With some modifications. So we're going to look at the modifications. We're going to talk about why we did them, and we're going to try to run it. So I'm just going to open up Visual Studio Code here to take you through the code. So let's start by the C file, and I'm going to show you. So this is a comparison between the two C files so that you know. So that this actually test bench, the Wishbone port test bench, is inside Caravelle user project because it's simulating the example project. This shouldn't be used. This should be used as a reference, not as a test bench for your design, because this is for another design. But it's a reference for you to work with. And actually this test bench is exercising the Wishbone, which is used inside our user project. So basically we start by defining the registers that Ziad talked about yesterday. So we're defining the X, Y, which is the multiplicand and the multiplier. And then the P0 and the P1, which are going to be our read values, or the product registers. And then we're gonna disable, like if you come here, this is enabled, and the SPI is enabled. We don't want the housekeeping SPI in our test bench, so we're gonna disable it. And then we're gonna configure our IO. So we want to configure from IO 16 to IO 31 to be output from the management. So so we're gonna configure these IOs. It's actually configured the same here. And then we're gonna load apply the configuration, the IO configuration. And wait till this register turns to 1, and then we're gonna start our simulation by emitting. So this is the low register. So this is executing, like it's putting this register value into the low bits of the IOs. And then we're gonna enable the Wishbone register because we wanna write or read. So whenever there's a write or read from the Wishbone, you have to enable the Wishbone register. So we're gonna enable the Wishbone register, and then we're gonna write to the multiplicand 10. And then disable the Wishbone register, and then enable it again because we're going to write again. So we're going to write 3 to the multiplier, and disable the Wishbone register, and then enable it again and read from it the product. And then we're gonna signal to the IOs that if the product is 30, then we're gonna signal to the IOs that and we're gonna put the values, put this value inside the low IOs, low bit IOs, and so that we can signal to the test bench to end. So let's go through the Verilog file. The Verilog file is probably the same between, not probably, actually it is the same between both. So here you're just defining the registers and wires that you're gonna use, and you're gonna put a check bits on the lower bits of the IO, so lower IO account, and then this is a design specific part, so you have to keep the IO3 high if you're not gonna use the SPI, housekeeping SPI, which does another functionality in Carvel that is not covered here. And then we're gonna put the half. This is the half period of the clock. So the clock here is 25 nanoseconds, because this is the half period. So it has a period of 25 nanoseconds. And this is the part where we load our SDF file. So remember, if we go back to our presentation, OpenLane emits the SDF files here. So you actually don't need to generate them using any tool. OpenLane does that automatically. So you're gonna have them, and I can actually show you where it is. So if we go back, all the way back, we're gonna see here that there's an SDF for the multiplier 32. So so we're gonna load these, and actually starting from here, it's constant between all designs, because this is loading the SDFs of the management core and Carvel. This is not really clean. It's gonna be cleaned up very soon. But basically, what you need to do is to change the SDFs that belong to your project, which is here, for example. So if we look at the Verilog from the other wishbone test, we're gonna see that it's the user project example. So I changed it to have our user project example, our user project, and the rest is constant. And then here we're dumping the VCD file, which I'm gonna cover later. And then we're just waiting. We're putting a delay until the test bench might time out, because if the passing criteria doesn't happen, then the test bench is gonna time out and fail. But if the test bench if the passing criteria, which we have here, which is the last thing in the C code, which looks if the product is 30, which is like the right product, which this is the passing criteria. So we're checking for the passing criteria, and if it's passing, then we display a monitor that it's passing and finish the test bench, finish the simulation, I mean. And this is just a monitor to just display that the first criteria happened, which is this flag, and the rest should be constant between all test benches, because this is loading Carvel and the Flash. Okay, so let's go ahead and try out this test bench. Oh yeah, something that still didn't cover. Yeah. So we covered the first file, the first step of doing our functional verification. Now we need to do the second step, which is changing the includes file. So if we go here inside Verilog, we're gonna find an includes directory, which has 3 includes files. So there's an RTL gate level plus SDF and gate level includes file. So we're gonna run the RTL now. So we should include we should modify the includes here. So so I already did that, but if you open that file right now, you're gonna find that it's not like that. It's actually including the user project example. We should remove that and include all the macros that we have inside our design. So that means that we have the user project mul32, the SPM and mul32 Verilogs. This is a crucial part of the simulation because this is what the test bench is going to be loading in order to do the simulation. I'm gonna pause here for a couple of minutes, not a couple of minutes, but for like a minute. So if you want to take a look at it and modify it. Okay, so basically now we're done with the first 2 steps. We now wanna run the actual test bench. So it's basically just one command that's gonna run either RTL gate level or gate level plus SDF. And for the sake of time, because we don't have enough time to run either gate level or gate level SDF, because these take a while, as I said before. So we're just gonna try out the RTL now. Make verify wishbone SPM dash RTL. So basically, if you wanna run RTL, I'm gonna write dash RTL. If I wanna run gate level, I'm gonna write dash gate level, and so on. I think this is gonna take a while, so it's not gonna take a while, but I don't want to keep you all waiting. It's gonna take like a couple of minutes. So basically, if we're gonna see a monitor, either it's passed or failed. So this is how the monitor is gonna look like. So if it's passing, and so actually this monitor can be seen here. So this is the monitor that's going to be happening if it's passing. And there's going to be a VCD file getting emit from the test bench. So this VCD file is basically the file that has all the waves in it. So if you want to debug and see what's happening inside your design, you can look at this VCD file using a GTK wave and take a look at the waves, take a look of how your user project is interacting with Caravelle. You can take a look at all the Caravelle waves if you want to, which you should you probably shouldn't need to do that, but if you do want to look at it, you can. So this is going to be under the test bench directory that we were just seeing. Okay. Moving on to physical verification. So physical verification has to do with LVS, DRC, ERC checks. Okay, so there's the LVS, which is layout versus schematic. So basically, now I'm done with my design. I have a layout, which is the GDS file. I want to make sure that this layout matches what I was just verifying right now with the gate level netlist. So basically, the LVS check does that. It verifies that your layout matches the gate level netlist. And then you have the DRC, which is the design rule check. So this check basically basically makes sure that your layout match like your layout doesn't have any shapes that that the fab can't manufacture. So there's a set of rules that the layout should have, like for example the spacing between metals should be of a certain space. So so the DRC basically tries to look for these issues, and it's going to report if you have any DRC issues. And that check basically makes sure that your design won't have any issues when being fabricated in the fab. And you have the electric rule check. And actually all these physical verifications are done through OpenLane, so you don't have to do it off of the flow. It's done there, and it's gonna break and tell you that you have an LVS, DRC, or ERC violation. And actually, because of how important it is, pre-check does DRC using two open source tools, Klayout and Magic. And there's a redundancy here because with open source tools, we want to make sure that the tool itself doesn't have any bugs. So we want to make sure that there are no checks that weren't done or were done in the wrong way, or there's a bug in the tool. So we always try to have redundancy in our flow. So pre-check is actually going to fail if any of them fail, and I'm going to talk about pre-check actually in the next slide. And then there's tape out, which we talked about earlier, which is going to do a DRC check on the whole chip, including your design inside it. So it's going to make sure that your design can 100, not I can't say 100%, but 99.9% can be won't have any issues when being fabricated. This doesn't have to do anything with your design specifically. It has to do with how your layout looks like and manufactured. So now going through, now I have the layout. I did the verification, I did timing simulations, I did everything. My design is clean, and I want to go ahead and submit a project. So basically, before you can go and submit on the OpenMPW shuttle, you have to go through a couple of steps to make sure that your design can be integrated smoothly with no issues. So pre-check is the first check that we do once we get your design in. So pre-check checks for a few things. It checks for your license, that you have all the licenses in your directory, and they all are open source and not prohibited. Remember that you have for you to get on the OpenMPW shuttle, you have to have an open source design. You can't have a private design. So so it checks for these licenses, and then it checks on makefiles, so it shouldn't be changing anything in the makefile. So that's one thing. And then it checks that the defaults check is checking that you that the design that you're submitting is not the default project we have, which is the Caravelle user example, the user project example. And then it checks for documentation. You have to have a documentation. You can't have an empty README file. And you can't use any like bad language. Bad as in non-inclusive language. And then there's the consistency check, which checks that your netlist abides by the golden wrapper, your user project netlist and the Caravelle or Caravan netlist. And then you have the XOR, so the XOR check, which basically makes sure that your design fits perfectly inside the hole that we have inside Caravelle, and it is and it doesn't have like any connections outside that hole, so that we don't have any issues when integrating it inside Caravelle. Then, as I mentioned before, we have Magic DRC and K-Layout DRC. And then you have K-Layout off-grid check, which checks if your design has any shapes that are off-grid from the layout itself, from the rest of the shapes. And then you have a metal density check, which checks that you have the minimum amount of metal density in your design. So there are two ways to do pre-check. There's a way that you can do it locally, and then there's a way to do it on the platform. I'm gonna go through the platform, but I strongly encourage you to go through the one that's locally, so you can go ahead and try these two commands out, and it's gonna run it automatically, and it's gonna give you like a summary of if you have any failures. And I'm actually gonna show you a failure that I have just to show you for the sake of this hands-on session. So actually, let's go to this link, which will take us to the platform. First thing you need to do when you're submitting your design is log in or sign up. So I'm already logged in. So when you're logging in, you just need or signing up, you just need your to go through like the normal sign up for any website. And then you can go ahead and start look at which shuttle you're gonna go on, and then you can start a project and fill out the details of the project, like the basic details. There's more details here if you want to add images and the address you want to ship your project to. Actually, I have that already done, so I'm gonna go to my projects. Okay, so when you start your project, it's gonna look like this, and you can go to your workspace, and if you click here, you're gonna start the pre-check. So actually, before doing a pre-check, you can't do a tape out. So so the first thing to do here is click here and start a pre-check run. So actually, I have two pre-check runs, one that failed and one that succeeded. So I just wanted to show you as a demonstration of how to see the failure on the platform. So going through the logs, you're gonna feel going all the way down, you're gonna see like what is the failure here. So the failure is the document. And then if you go up, you're gonna find like where is the failure, and it's gonna tell you exactly what's the failure. So here it's because I didn't have any documentation, and then I updated that. So now I can see that it's succeeded. And if we go through these, you can see that it's doing all the checks that we were just talking about, and that at the end of the log file, it's going to tell you that the check succeeded. And then once you've done that, you can go ahead and do a tape out. So basically what the tape out does is it integrates your design inside Caravelle, and it's gonna do some checks. One of them is a DRC check to make sure, and it's gonna do some fill insertion and other checks to make sure that your design fits perfectly and it doesn't have any issues when integrating with Caravelle. So actually, I have a tape out job here that actually that's actually succeeded, and you can see like the log here as well, and it's saying that you can find the logs inside your workspace here. Okay. So let's go through the Open Galaxy to see how my user project got integrated inside Caravelle. And actually, so one thing to mention here, if you have a failure here and you have like a DRC fail, sorry, and you have a, come on. If you have a DRC failure here and go to the logs, you're gonna see exactly where the DRC failure is, and it's gonna tell you exactly the path that you need to look at if you have a DRC. There's a marker browser for DRC errors, and I'm gonna show you how to do that. So now I opened the Open Galaxy, which is like a remote desktop, and I already did that, but you should git pull so that you get all the your designs inside the remote desktop. And then I'm gonna open a terminal, cd home, and go to my user. And I'm gonna go to my designs. Okay, so so this project is called Webinar Test 1, and then I have jobs, important repo. We're interested now to see the jobs. So you have both pre-check and tape out. If you want to look at the pre-check, I have two pre-check runs, if you remember, we have two here, and then I'm actually interested in looking at the tape out to see how my user project looks like. So it's inside Oasis. It's an Oasis file, not a GDS, which is exactly the same as a GDS file, but it's compressed. This is gonna take quite a bit of time because it's actually loading the whole layout of the whole Caravelle chip. So I guess I'm actually done with my presentation. So I guess we can take questions, and once this is loaded, I can go ahead and show you again.